And now we are going to introduce the classification of supervised learning. Okay. So let's look at a famous example. It's called iris flower classification. It includes only 3 classes, which first one is called iris versicolor, and then second is called setosa, and the third is called virginica. Okay, how can we classify those flowers? What's the feature that we can use? So first, we want to select some characteristics of the flower to classify their difference. One of the feature may be color, but the color is not reliable. So in this data set, we select 2 features: the length and the width of the sepal and the petal. Sepal and the petal, right? Okay. So for most of the machine learning, you need to extract features. So in old time, there are a lot of researchers have studied the feature extraction. It's called feature engineering. Now we use deep learning to extract features. So let's extract features of iris. We use the width and the length of petal and the sepal to separate the flowers. There are 3 classes. So here's how we can make data set. We can prepare our data. So it's actually you can put in a Excel file or CSV file, and then each column is the feature, right? The number of features, the length of sepal, width, and the length of width. So we have 4 features, right? We have 4 features. We have 4 features. So samples, each flower, each measurement of the flower is called samples, right? So each row is 1 sample. You can call it samples or instance or observations. And we have 4 features. Features are called attributes, measurement, or sometimes dimension, right? Dimension. So we have 4 features, right? And then it's supervised learning, so we have class labels, answers. Usually we separate our feature data with our class label, but you can put them together, depends on you. But usually we separate those information into 2 files. So now we this simple file is our first data set, and then we try to learn how to classify the model. So first we can try to visualize it. So we use the petal length and the sepal length as an example, because 2 features set is easier to visualize. In fact, we can only visualize 3-dimensional data, right? So remember we have 4 features, but here we only use 2 of the 4 features. And then we can plot our samples on this plan. Then you can see that there are 3 categories. One is versicolor, virginica, and setosa. So this data set has a feature that the 2 of the data are mixed together. So first we will try to find a line to separate those data. Right? Find a linear function. To be more professional, this line. So we want to find a function that draw a line that can separate the data. More professional is called linear function, right? Linear. Right? So we try to find a line. This data set has a feature that versicolor and the virginica are not linearly separable. So you can it's hard to find a line to separate those two data, right? It's not linearly separable. So it will make our learning algorithm a little bit challenge. But in practice, in high dimensional data set, it's usually not possible to find a linear plan to separate all the information. Okay. So this is one of the TensorFlow tutorial. So first, we try to find a binary linear classifier. Binary means there are only two classes, right? Binary means two. Oh, shit. Binary means two classes. You may wonder there are three, right? So let's group this together as one class. So then we can try to find a line to separate them, right? So it's called binary classifier. So let's try to find a linear function that can separate the data. So this is our first algorithm called the perceptron. Remember perceptron, right? Proposed by Frank Rosenbaum. Yeah. Then this is the first neural network. It was called perceptron. So here's a linear function. Linear function. First, please note that in this figure, because in geometry we usually represent the horizontal axis as x and the vertical axis as y, right? But here we do not do that. Here we represent our horizontal data petal length as x1 because it's feature 1, and the sepal length as x2, feature 2. Right. And each one has the weight. Y is the answer. Y is the answer. So the linear function, we see. How can I show the? Yes. Okay. So this linear function is when you have an input, it's a W1 plus X1 plus W2, X2 plus B. This function equal to 0, right? So we don't have our Y is X2. Right, for traditional geometry formula, there are X and Y, but now we only have X1 and X2. So we have a bias. A bias is to move the line away from the original point. So we can use a vector to represent the data. I will help you I will remind you the map later. So this is 1. Okay. And then you can use a bold symbol to represent the vector. So finally, we can write a WTX, which means the vector W multiplied by, it's a dot product, right? Vector W multiplied by the vector X plus a bias. So if a new input X is coming, and it will calculate a new value y prime. If the y prime is larger than 0, then this belongs to the right plane. If the y prime is less than 0, then it belongs to the left plane. Right. So y is the prediction. It's not part of the axis. So perceptron, first we want to calculate the difference between prediction and the true label. We usually make a square, which is called the mean square error. Mean square error, MSE. Because we have multiple y, right? We have only one y, but we have multiple input. We have multiple training data, multiple x. So then we sum of the square and divide by the number of n. It's 1 y1. We have multiple samples, right? Multiple flowers. So we have multiple predictions, and we just calculate the mean of the square error. We love mean square error because the differential of the square, the differential of a function square is equal to the function. All right. From the multiply the, yeah. Is that a true earthquake alarm or drill? So I think maybe we should dismiss the class to imitate the earthquake drill, right? Okay. Yeah. So if you want to calculate the gradient, right, the gradient will become will just become a y minus y prime. Right. Sorry, my pen is broken also. I can really only use my finger. So we want to calculate the gradient of our function. And the gradient is called the differential. The gradient helps us to find the direction of our the direction to adjust our weights. So yeah. So y prime is our prediction, and the y means the labels, and then we just calculate the difference and the update error. So let's see my original formula. So L means the loss or cost or error, whatever you want. L means the loss function, and the gradient delta L is just the y minus y prime. We omit the constant too, and then there's a loop. We just use the gradient. We just want the direction and multiply by a learning rate alpha. Learning rate depends on how much we move, and then we update our formula. Descent, maybe this should be minus, but yeah, it should be okay. Okay, so let's update our weight. We have 2 weights for each feature. Update the weight until the loss is small enough. So that is how we train a linear classifier. It's called perceptron. You can implement the training process in Python. You do not need any framework. Maybe our first homework is to implement perceptron. Okay. Yeah, good idea. Next week, I need some time to prepare data set. I find that Kaggle homeworks maybe is too easy for you. So maybe we should have more challenging homework, like develop algorithms without any deep learning framework, right, to help understand the real machine learning, and submit to GitHub. This is my idea, but I need to try it first. Anyway, the perceptron is a simple and useful algorithm, but the performance is not good. And it did not answer a question, which line is the best one to separate the data? Or in other words, which hyperplane? Line is only for 2D plane, right? For high dimension, multiple features, we have high dimensional data, then it's called hyperplanes. So which hyperplanes has the largest separation? So support vector machine says that the best line to separate data. So in this example, as you can see, we can have multiple possible lines to separate the data. We choose a color. There are multiple possible hyperplane to separate data. Which one is the best? Which one is the best? So SVN says the one with the largest separation, largest margin between those two data is the best plan that we can use. So there's the margin between those two data sets. So first, the SVN will try to find the two hyperplanes, or the dashed black lines, two hyperplanes. Or say support vector, they say it's a support plane. Suppose the hyperplanes. Anyway, you know idea. So that's why it's called support vectors. Finally, they choose the plane as the 1 and the -1. So the class label now become 1 and the -1. 1 is -1. Originally is 1 and 0, right? So the blue class y is 1, y is -1, and then you can calculate the distance between those two planes using the norm, 2 minus norm. It's about geometry. So loss functions is called hinge loss, or hinge loss. The hinge loss means that we will review it details in the following class. But right now, you just need that we need to make sure that all blue dots, the feature of all blue dots input into our hyperplane will be larger than 1. Then there's a correct classification. If the input is less than 1, then we should give them a penalty, give them a loss. If we successfully classify the input, then the loss is 0. Right? If we fail, the far away from the more distance the data is far away from the hyperplane, the larger the loss. The larger the loss. The idea is like that. And this is the same. For the green data set, the input text should be less than the hyperplane. So the labels now is 1 and the -1. Okay, this is a support vector machine. This is one of the most successful algorithm before deep learning. So this is an optimization problem to find the largest margin. So the optimization problems first need to have an objective function and then more details. I should move these details to another class, but that's just knowledge. There's an algorithm called SVN, useful and belong to can be used for mainly for classification. Belong to the analogizer branch. So Oh, okay. So we now know SVM can find the best hyperplane, but the problem is how can we separate nonlinear data, right? Remember that the versicolor and the virginica, we cannot separate those two data if we just use a line. So how can SVM solve this problem? SVM has a famous trick called the kernel trick. Kernel trick. So the idea is that if the lower dimensional space, like a 2D plane, cannot separate the data, we can project them into a higher dimensional data, and we hope that in the higher dimensional data, we can find a hyperplane to separate those two group of data. Just hope. So in old times, we spend a lot of time to calculate the kernels, but it's slow and not efficient. So not popular today. So they Scikit-learn wants to convince us that the nonlinear kernel can indeed create some curve, right, in the data separation. So it's SVM, there are some RBF kernel which is similar to Gaussian kernel and the polynomial kernel. So you can create some curve. But for deep learning, is naturally can learn nonlinear plane, right? So deep learning is much naturally can separate nonlinear data. So I guess I spent too much time to introduce SVM, but yeah, it was a good algorithm. So another problem of SVM is that it's used for separate binary data. Right? So far, we are handling binary class. We have 3 classes, but we group 2 of the class together, become 1, and then we can focus find a plan to separate 2 data. So how can we handle multi-class, perceptron or SVM? The answer is, the first way is to find a classifier for each pair of the data set. Right? So suppose we have 3 data sets, then we need to find each classifier for each 2 of data. So we find the classifier AB. So we find maybe CAB for classify A and B, and CAC. So we need to learn 3 classifiers. Right? This is not a good example. So anyway, for n of class, we need to find a Cn divided by 2. This formula means n multiplied by n minus 1 divided by 2. All right. So you need to find a classifier for each pair, every pair of the classes. However, for 3 classes, the number is equal to 3, right? 3 multiplied by 2 divided by 2, so it's a 3. And the other one is 1 against the 1. Is what we have done in previous class. We just group. First, suppose we can group A, B, C together to become class and find a class to, for example, classifier C, A, B, and C, right? So in this case, you just need to unclassifier, right? Unclassifier. Just select one class and make all the other classes the same group and find a classifier. Unfortunately, in this, so you can see that 1 against 1 will need much more classifier or spend more time. But in this example, it happened to be that both methods run 3 classifiers. Okay, anyway, we don't care them in deep learning. Just call TensorFlow or Keras, PyTorch. Anyway, so finally go back to neural network. So how can we use neural network to learn the classifiers to classify data? So first, you can see that the neural network can naturally accept multiple inputs. In previous one, we can usually accept the multiple features. Or we just, in previous example, we use 2 features because we want to visualize them, visualize the classifier. So yeah, the input is the feature, and then we go through multiple hidden layers here. Right, huh? How many depends on how many you want to use, and each layer, each neuron is connected to other neurons in the next layer. And finally, we can use a layer called softmax. Softmax calculate the probability of each class. So for softmax function, softmax function. So each, and you can see the probability of each class, right? Each class of iris. So it can be naturally a multi-class classifier. In previous one, we learned binary classifier first, and then train multiple binary class. But neural networks can naturally become a multi-class classifier, and then the softmax calculate the probability of each class. The input data belongs to which class. In this case, versicolor has highest probability, so we suppose the input is a versicolor class. Okay. So selecting features, although today we usually put raw data into neural network and ask the framework to learn the features for us, or we use pre-trained data set, pre-trained model to extract features. But feature engineers is still very important. Here's an example. So the data processing process includes 3 steps. One is called vectorization and normalization. Okay. And yeah. And we need to handle the missing values, and feature engineering. But here's examples. If we put, suppose we want to recognize the time from an analog clock. One way to represent the position of the pointers is that you can use the XY. XY position is to represent the clock hand, represent the position of the clock hands. However, you can use the theta because they are running in circles to represent the position, represent the angles of the clock hands. If we use theta, then we only have 2 features. If we use the XY position, then we have 4 features. Right. So for some data, you can try to find a way to represent your data more efficient. If you have less data, then it's easier for your model to learn the better algorithms. Okay, so the next one, we want to talk about the naive Bayes algorithm. Remember that the naive Bayes is about the conditional probability, right? So it's pronounced as the probability of Y occur given X has occurred, event X has happened. So event X can be a vector, or the value can be a vector. So it's usually we use X to represent input data and Y is the label, as I said. And the conditional probability, let's quickly review it. That P of Y given X is equal to P Y and X divided by probability of X. Right? This is called AND, which means Y and X both happen at the same time. So now you understand why this formula is equal, right? Because PYX multiplied by P of X is equal to Py and X. Py and X usually just Pyx, huh? Pyx. And it's the same as P of Y given X multiplied by Py will be equal to P, sorry, I mean Pxy, huh? Pxy multiplied by Py will be Pxy, huh? Pxy is equal to Px and Y happen is the same as Y and X are exchangeable. So those two formulas are equal, huh? If you just move this term to here, you can see that it's an equation. It's an equation. So the probability of Y is the distribution of your class. It's called the prior knowledge because we already knew the distribution of our labels, training data distribution. So it's called prior. And then the P of X given Y happens called likelihood. And the P of X is called evidence, but usually we can omit it because this number is the same for all the class. So this about input data. So we usually can when we calculate probability, we can omit this number, huh? Okay, so yeah. Oh, it's empty. Oh, okay. Next step. So base as we know, the input X is a vector, so it can be separated by multiplication of multiple features. So here's an important assumption. If the input features are independent, then we can multiply all the features together. We can turn this formula into multiplication. This simplifies our training process, our representing process. If you calculate the log of the multiplication, it becomes an addition, right? It's very easy to train. So naive means simple. Yeah. So why it's called simple? Because it makes the assumption that all the features are independent. And this assumption is very strong because for complicated data like image, usually the features are related to each other. So this is not a good method for image, but it's useful in some other problem like spam filter or email spam filter. So that you can now turn this conditional probability into multiplication for each feature. And then as I say, we usually omit the denominator, numerator, and then remove the P of X because it's the same for all class. So it's directly, we use this formula to train. And we'll try to maximize the probability for the correct class. That's naive base. Okay. Okay, so this is how you. Another one is that you need to make assumption of the underlying distribution, probability distribution of your function, right? If you don't know which distribution to select, just select the Gaussian distribution. Yeah, but yeah, so you can use how to use the naive base in scikit-learn, or it should be simple. First, you load the iris data set, and then you import the Gaussian naive base classifier. Then you feed the data. The data have target. So the label is called target in the scikit-learn. Watch out. And then we feed, and yeah, then we can make prediction. Then you can calculate the accuracy. So I guess you must wonder which one is best. What kind of classifier is best on the iris flower data set, right? Good news is I have done the experience for you, and here's the notebook link. Also, let's take a look of my Colab notebook. So in this slide, you can play with a notebook. I have run all the models using scikit-learn. So first, you need to find a matrix to measure the performance of your model. So import the linear model. SVN linear model has the perceptron. And the K-near is the neighbor. Naive Bayes. And that's it. So first, load the iris dataset. Good. Can you see it clearly? Are you still awake? Cheers up, cheers up. We can dismiss class earlier, right? So let's demo today. And yeah, so I suppose you can do programming. So we can load the iris dataset. It has been prepared by scikit-learn. We just don't need to download data. Of course, it has been pre-processed. If you want to watch the flower pictures, I'm not sure where to find the flower pictures, but the width and length, the features are saved on the cloud server. Also, we can download it. And then the X is the input data. Y is the label. They call it target anyway. So we can show how many X we have. There are 150 training samples in the iris dataset. Actually, there's all the data in iris dataset. They didn't split the data into train and the test. This is not a good practice. But because we are newbie, that's fine. So let's choose some parameters. They are called hyperparameters because they are not parameters in your model. But what is hyperparameters? It's like the number of K you want to use. Okay, you want to use the regularization number. If you want to get best results from your model, you can tune the numbers. But here we just set it to 5. So okay, and then at 5. Another variant of K enhanced version is like you can use the distance as the inverse of distance as the weight of the neighbor, right? If the neighbor is very close to your input data, then it should be more important. It looks more like the neighbors, or should have some higher weight. So weighted KNN and perceptron. Also a regression method. Regression is for continuous data, right? But L1 regression is for classification. We will learn it later. And the linear support vector machine classifier, so it's called SVC. And then naive Bayes. So training. Now we can start training. We have a loop. We can call each classifier, and all the classifiers inherit from the same class. So it has a fit function. Just call the fit function, pass the input data X and the label Y, and we can make a prediction. So it's a prediction on training data set, but it gives you a peak of the performance. So KNN at 5 is it's good, but weighted KNN is better, 100% accurate, but it's common on training data set. Perceptron terrible. One of the reasons is that we haven't tuned the data set, but the perceptron usually doesn't work well. And logistic regression good, linear SVC, and naive Bayes. So if you want the baseline model, weighted KNN is a good choice. Simple, you do not need to train the model. Yeah, and yeah, okay. So yeah. In fact, Google has prepared a test data set for iris flower because they have a tutorial for TensorFlow. So we can download it and test it. 30 testing samples, so test our models. KNN still 100%. Great. And weighted KNN perceptron has been improved. It's unusual that a model perform better on test set than train set, but it's possible. Training data set or training set. It's possible. It happened. It's receive 100% because we have much less samples, right? Only 30. So SVN was good. Finally, I add the 3-layer DNN model. The result was reported by Google tutorial and show this picture. For small data set, actually, neural network does not perform better than other algorithms, and it has much more parameters to tune. So that's why it was not popular in old times. But today we know that what deep learning can do, and everybody are buying GPU. So yeah, so that's a result of classifier evaluation. So go home and play with the notebook. Okay. So let's take a break again. Let's take a break again.